Yeah. And now we are gonna transition into a world that spans the Windows and Linux. And Mukul from Microsoft is gonna tell us about their journey on porting production profiling from Windows to Linux.
Hi, today we're going to talk about porting BPerf from Windows to Linux. My name is Mukul Sabharwal. Just to give an overview, we're going to first cover what production profiling is, what are its use cases, what is BPerf, our production profiler, how it relates to ETW, and porting BPerf to Linux. Continuous production profiling is basically a 24/7 fleet monitoring system that is looking at profile data as its main source. The profile data can be coming from various physical sources like CPU, memory, disk, or it can also be synthetic logical things like context switches or application-defined events. And the main idea is that you don't perturb the fleet that you're monitoring, so you have to sample it, but get enough samples that it's statistically significant. So the main use cases for production profiling for us are debugging production incidents. So if there's a runaway thread, there's some particular piece of code that's allocating a lot of memory, or there are hot functions that need to be looked at because they're consuming too much of the CPU. These are all cases where a incident debugging system is useful, and therefore this is our top use case for BPerf. Improving app code performance. So looking at aggregate profile data, looking at single request view, or region of interest for your application are common tasks that developers do. And finally, using this data for training profile-guided optimization. There are many tool chains out there that can take input as profile-guided data, and then as long as you can talk to that format, you can take production data and feed profile data to your tool chains and get profile-guided optimizations. BPerf is basically a continuous production profiling system that we built on ETW. It is foremost a CPU sampling profiler. That means that it is looking at CPU sample data that's coming out of the operating system. Instrumentation like TCP/IP file I/O are other important instrumentation points that it listens to, and then framework instrumentation from .NET, shared libraries, and finally application instrumentation, when applications can mark their regions of interest with start and stop events. BPerf also discovers ambient causality chain, so thread transfers. When you have code executing on thread 1 that switches to thread 2, if they are done in a specific framework, for example, if they use particular APIs like the .NET APIs for async await, that causality chain can be maintained. We can also listen to assist information from the application that can stitch causality information together. So for example, if the application has a really custom way of doing thread transfers where they maintain their own queue, they can instrument those queues and they can tell us about how the work was transferred from one thread to another. This helps in maintaining the causality chain. And then finally, hardware counter data, which is often useful for power monitoring, instruction cycles, instructions retired. All this information also comes out through ETW that we monitor. And then finally, the output of all this data, this incoming data, can then be aggregated and made as top-end functions. So for example, which are the 5 or 10 hottest functions that are executing right now, and some other number of operations per second for a custom defined event, for example. All this information can be output when we're listening to all this data. And then finally, all the different kinds of events that are there, ETW provides a nice way of collecting call stacks. And so BPerf listens to those call stack data and then can emit that also. And then finally, the data center-wide canonicalization of these instruction pointers. So these call stacks are made up of instruction pointers. Obviously, these instruction pointers are only valid in the context of the application, and then they have to be canonicalized to function names that are useful for developers. So what is ETW and how does it relate to BPerf? ETW is a common framework for instrumentation in Windows. It is an umbrella term for many different pieces that are provided by Windows. The most developer-centric piece here is the entry points that ETW provides that applications link to. So when applications define their events, they eventually link to a library provided by Windows that then will actually emit the event. ETW also provides operating system-wide services that maintain state for event delivery. They maintain the per CPU buffers, which events are enabled or disabled, and which sessions or controllers are actually emitting those events and who is allowed to listen to those events. ETW also has schemas, so event schemas for different kinds of events that you can define and then have and extend them, and there's a well-defined format for that. And then finally, there's a file format. This is not the file format we end up using in BPerf, but this file format has ideas that we do leverage. For example, self-describing capabilities, and tools and ecosystem that can operate on these files. Finally, ETW has two distinct ways of delivering data. One, where the operating system can write all these events that you may have enabled onto a disk at a file location specified, or they can be delivered to a real-time application that is listening to these events. The key advantages of ETW are that it's homogeneous instrumentation in the Windows ecosystem, and the fact that it has a self-describing data file. And the disadvantages, obviously, is that it's Windows specific, and therefore, if you want to use in Linux, you have to do some sort of porting exercise, probably carry some concepts because the file formats and obviously the other functions are Windows specific. And even though I mentioned the file format initially as something that we leverage, we actually leverage mostly the concepts, and the actual file format is not very amenable to production scenarios. This is a high-level architecture that I got from MSDN about ETW architecture. You have controllers, providers, consumers, and then listeners. Controllers are basically these applications that are starting and stopping sessions. Providers are groups of events. So an application could be an event provider, and then it could have different events. And then these per CPU buffers are maintained by the Windows kernel. And you can either consume the events through this on-disk data, or you can be a real-time listener, which is what BPerf is, and then get the data that way. So now that we've talked a little bit about ETW, what exactly is BPerf in relation to ETW? BPerf essentially is an ETW listener, and it listens to operating system instrumentation, application events, and various other framework events that are being emitted by already instrumented applications. Each event is then delivered via a function callback. This is the real-time mechanism of ETW, and the callbacks are buffered up to X events or Y milliseconds. So for example, we'll buffer 10,000 events or events that have transpired in the last 2 seconds and then compress and write them to disk. As I mentioned, the file format is actually key to this, and we make sure that we also have an index, basically a way of skipping data that we don't deem necessary to be valuable to certain scenarios. So a common one is a time index, so you can skip into various parts of the file. So if you know that the event occurs at a particular time, or you're looking for data within a subset of an interval, then you can basically not have to do I/O for most of the data. The self-describing part of it is also very important, where the schema of the events is part of the event stream, and it always appears before the first event of that schema is ever encountered in the stream. This allows you to have a self-describing decoder that just needs that specific file of data that you're looking at and can be essentially analyzed anywhere in the cloud, on different operating systems, without any specific thing tying you to that particular version of a particular build of Windows. And then we do other important things that are needed to reduce I/O. For example, doing delta compression for timestamps, which makes a lot of sense, but also doing delta compression for instruction pointers, which is surprisingly very effective because a lot of times functions have locality, and that will help you reduce the range of integers that need to be compressed, and therefore delta compression becomes very useful. And then finally, one of the most pivotal pieces of BPerf is the efficient symbolization. Symbolization is basically taking the instruction pointers to function names, and this is an expensive process. Whether it's being able to decode this data because of all the symbols that you have to go through, or the JIT code information that you have to parse through. Symbolization is actually a very time-intensive and CPU-intensive process. So what did we when we started to think about porting BPerf to Linux, exactly what were the parallels from ETW that we saw in the Linux ecosystem? The first one is that the Linux ecosystem has different ways of doing instrumentation in the user mode, but in the kernel, there are trace points and kprobes. And what we learned was that trace points are well-defined across kernel versions, and even though that's not a guarantee, that it seems to be something that you can rely on. But as I said, since we do have our self-describing format, we do actually, as I'll describe later, leverage the schema that is available on the particular kernel version and embedding that so that we don't actually have to rely on the versions of the trace point. On the user mode side of things, uprobes are what we realize are much more powerful than the Windows equivalent mechanism, but they are also a bit more complicated to use. So you end up having to use library like systemtap or something equivalent. But from the kernel's perspective, what we realized was that essentially it requires an elf file and an offset in that elf file to instrument. But obviously the instrumentation that the kernel does, where it swaps out instructions, have to be something that are valid. So there are some precarious conditions that you can run into, so you have to be sort of careful, and therefore using a library really helps. And then when we surveyed the ecosystem, we also realized that there are some benefits to use to perf events and eBPF that are lacking in Windows. For example, the perf events ring buffer notification for overflows can be exploited to do much more efficient delivery than compared to ETW. And BPF maps provide unique opportunities for doing in-kernel aggregation. We use this mostly for implementing Windows-style performance counters. And there are certain other helpers that BPF provides, like BPF get stack ID, which can provide stacking churning, which is useful if you wanted to just not have a lot of data being transferred from kernel mode to user mode. So what we did is our take one was actually understanding what parameters we would like perf or perf event open to have. And so we described a JSON schema that I've described here that tells you the kinds of things that we want. So we want a software event, we want to look at CPU clock, and what kinds of flags. So this is if you're familiar with perf event open, you would see that these are parameters that are needed for that function call. So our first thought was, why not just use perf? So, which is the tool that comes with most Linux distributions. The high-level design here was we start a process, perf, with the desired options and run it for X minutes. Then when the data collection is over, we convert it to a text format, and this text format is then converted to our file format that is needed by the rest of our systems. The advantages here are pretty clear. You're using stock tooling. It's easy to roll. The high-level design is pretty simple. And any benefits that you get from using a maintained tool, like new features, fixes, different tools, that an ecosystem that can read the perf.data files. But we quickly realized that there are significant downsides to running this in an at-scale system. The first is that the perf record, perf inject, and perf report at scale is very I/O intensive. That means you're recording all this data, you're potentially injecting all the JIT information that is not in traditional ELF files, code that is not in traditional ELF files, and then actually generating the report. All of this takes a lot of I/O. And then all the symbolization must occur on the target machine. That means you have to have symbols for all the code that you are running on the machines, which a lot of times you may not have. And then there's sort of JIT code has poor support. Obviously, this is getting better with perf inject. Otherwise, you have that sort of perf map files that can be used. But as far as we know, the perf map files are not something that can support line number information. If you know otherwise, please let me know. But from our perspective, it's only useful for doing instruction pointer names, but you lose a lot of information. And then finally, we would have to convert all of this to our file format, and that's extra I/O. So we thought, while there are benefits to using perf out of the box, that there are significant disadvantages to our at-scaled system. Therefore, we had to come up with a different approach. So the next approach that we took was, what if we just called perf event open and implemented perf-like tooling? Now, this sounds like a lot of work, and it actually is. But it has some surprisingly useful benefits that I'll talk about later. But basically, what we did was pre-existing trace points provide kernel instrumentation, which is satisfactory for use cases. So we don't actually have to end up doing K-probes. And as I described, we have our self-describing file format. So what we actually do is, when a trace point is enabled, we look up its metadata and insert that metadata into the event stream prior to any trace point of that being activated. So now we have self-describing trace points. Our uprobes for user mode events are also something that we wanted to leverage. And this is actually for most of the user mode instrumentation, whether it's different frameworks or our own application information. And code that's in ELF modules is supported as per usual. But JIT code requires runtime assistance, in our case, .NET. So we actually have to conjure up an ELF file, and that ELF file is then generating a trampoline. That trampoline is actually what gets uprobed, and then that information is put into our instrumentation with self-describing in self-describing format. And then finally, the symbolization is the key piece, which is where we get the biggest bang for the buck by ruling our own. So perf.mmap has special case handling, where we look at the build IDs, but consult our site tables where we may have already seen those build IDs prior. And this actually happens very frequently. When you have the same processes or similar processes, like let's say you have hundreds of .NET programs, very similar ELF modules are going to be loaded. And every time having to open up the ELF module to look at build ID actually adds a surprisingly large amount of cost, both in CPU and I/O. So we can consult side tables without actually having to go and open up the ELF files. And then the key lesson that we learned here is that our system for monitoring this must be started before the processes that we're monitoring. This sounds mostly intuitive, but actually you could have other ways of getting at the mmap data by looking at proc-pid information. But proc-pid information we have noticed sometimes is either lacking or incorrect. We're not quite sure why, but that's why our monitoring system, when it starts prior to all the processes that we want to monitor, gives us the best result, where we don't miss any symbolic events. And then JIT code obviously requires out-of-band injection of data. We can't get away with that, but our file format is robust enough to support putting this data at the end of the file or in various different points. So we can basically do this out-of-band without having to do it as we're collecting the data. For processing the ring buffers, as I mentioned earlier, perf events can provide you a surprising amount of flexibility, so you can do multi-threaded reads of these ring buffers. And we don't yet do that, but we do these triggers when a ring buffer overflows. We can actually go look at this data in a multi-thread fashion. We do it single-threaded today, but that is something that we're looking at. And then finally, here's where BPF programs like BPF get stack ID and BPF helpers can help us reduce the volume of data that is going from kernel mode to user mode. So just getting a little bit more into the mechanics of how this is achieved. First, you obviously have to set R limit to make sure that all your limits that are needed, from whether it's memory that you need to be able to allocate, can be set to limits that are valuable to your program. Then you have to load all the BPF programs. So the configuration comes from JSON, as I described in one of the earlier slides, and then we set up a per CPU perf event. So this can either be outputting to BPF, or it can be a dummy event, and this dummy event is useful for setting up the mmaps. And finally, once these perf event file descriptors are available, we then associate them with the ring buffers by just calling mmap and then providing the file descriptors. These set up what are called per CPU ring buffers. And then finally, we can take the per CPU ring buffers and redirect their output using perf event IOC set output to have multiple events send all their data to these per CPU ring buffers. So we don't actually end up spinning up a ring buffer per unique event. All the different events that we want to monitor end up going to a single per CPU ring buffer. This amortizes the cost of actually having to e-poll each ring buffer. And then you obviously have to enable these, but then e-polling all the FDs gets you this capability of potentially excavating or draining the ring buffers in a multi-threaded fashion. We right now only do it in a single-threaded way. And then we write it into our format. I described how we use BPF, and this is something where we are still exploring different ways of doing it, but what we realized is that we want to be able to, the BPF ecosystem is robust, but a lot of the ones that are more mature require having Clang and LLVM be something that you have to deploy. We are obviously tracking BTF core, but for the time being, this image describes how we write our BPF programs. We essentially have all the definitions that are needed from the kernel for the particular architecture available. So we'll define the PT-regs, and then this information is available to our authors of our BPF programs, who then utilize this, and then a special build of Clang that has only the BPF target to reduce the size of the Clang build is used for our BPF programs. What we're thinking in the future is, can we write the BPF programs in C#? First of all, is it really worth it? We're serving our BPF program authors to see is it something that's really valuable. But if it were to be, then we would have to write an MSIL to LLVMIR conversion tool. And then we would still have a dependency on LLVMIR. And should we just ditch our custom loader and use libbpf? A lot of this infrastructure was built while libbpf was still in significant churn, so we didn't actually take a dependency on libbpf. But things have matured since we actually we implemented this, so we could potentially use libbpf. And what does it buy us, and what do we lose? So the final thoughts. A key lesson that we learned when converting our infrastructure from Windows to Linux was that things that we had to optimize on Windows, we kind of have to do that on Linux too. So our symbolization infrastructure being the core focus, we had to optimize that on Linux as well. The perf event open syscall provides all the infrastructure needed for us to be able to do the optimizations. And we think that there are optimizations that the regular perf regard tool can use. So the work that we had to do to build our essentially similar perf tool could be incorporated into perf as well. And we are particularly excited about debug infod, the symbol server infrastructure that Red Hat is open source, and that we believe that a lot of people will rely on this infrastructure to be able to not have debug symbols on the target machines. These debug symbols can be very large. For many purposes, they can, for many organizations, debug symbols on target machines when running in untrusted environments can be a downside, and for trust and other purposes. So having these be elsewhere in a secure location is attractive. And then finally, we ran into one particular things with uprobes and jittered code, and there are some workarounds. The workaround that we use is that we create these dummy ELF files. There are also memory watch points that we explored a little bit, where you could have read-write memory watch points and then have that be something that can trigger for jittered code. We haven't gone down this a lot because we believe there's a limit for the number of watch points that can be there, since it's backed by our hardware registers. So we're not exactly sure how this will play out, but those are our next steps that we're thinking about in our journey to port this to Linux. Finally, this is an appendix. BPerf is open source. We do still practice and do all our coding in private, and then do a dump of the code in public. But we are trying to get better at that and actually do all our work in public. And then some of the other things that I described about with ECW and UFROs and trace points are available. And obviously, Brendan Gregg's perf site is a valuable resource. I hope you enjoyed this talk. Thank you.
Thank you, Mukul, for an awesome talk. It's great to see even more performance tooling available on Linux machines, and especially since it's coming from such a rich experience as Windows. And we have a question from Mani. He asks, how does this compare to XPerf that used to ship with Windows?
So XPerf is basically a tool on Windows, just for the audience, that can record performance traces. The key contributions to BPerf that BPerf makes in this area on Windows is that obviously collecting the data you can collect through any tool, but we have changes in the file format, the ability to do statistics and look at aggregations that we do as a real-time listener, which is difficult to perform using the standard tooling. And we believe this is a great area in our Linux journey because these are things that can be done more efficiently on Linux than on Windows.
Awesome. What would you say are the biggest challenges of maybe the ecosystem or the implementation of BPerf on Linux?
So I think the big challenge, Microsoft, we are definitely embracing more and more Linux, and as things, one of the challenges is that when you are working for a corporation like Microsoft with a long history of Windows, lots of things have been standardized. But in the Linux community, there's a lot of different variety of tools, So the big thing for us was picking the best in class, also making our own contributions, and then leveraging things that we believe are pretty good on the Windows ecosystem. That includes standardization, symbol servers, symbolification. That's had a pretty rich tradition on Windows. So marrying that with Linux has been the most sort of exciting thing that we are focusing on. And there's obviously Facebook and Google and others do a lot of work here. So we hope to contribute in this area as well.
And do you have any plans to, maybe since you mentioned standards and all that, do you have plans to also adopt things like open tracing or open telemetry?
Yeah. So for all the things that are ultimately as metrics, open tracing and those kinds of things, like which is the Prometheus formats that has become more standard now. Our goal is to integrate all that back so that we're not inventing new formats. The goal basically is how can we leverage the formats that are there, and if there is something novel, to bring that open in the community without and testing it obviously at our scale and then bringing that to the community.
Awesome. Well, thank you so much, Mukul. Since we are criminally out of time, I'm gonna have to ask all the attendees who have more questions to just direct them to the Slack channel. But fortunately, we are gonna have you for the panel discussion later today. So I'm really looking forward to continuing our conversation and see how we can, share our experiences even further.